Welcome, everyone. So let's get started. This is Serge Leontiev. I'm a product marketing director at Scylla, and I will be your moderator today. I enjoyed interacting with Kirill Alekseev in the speaker lounge during our last Scylla Summit just a few weeks ago. At the Scylla Summit, he had to cover all the things that Mail.ru did with Scylla in just a short 12-minute talk. His presentation was quite fascinating. It was about how that we at Scylla considered to be an unorthodox approach to using Scylla as a high-performance data store with a single-digit millisecond latency that scales out on a commodity hardware such as hard drives. So we're very glad to have him back today so he can spend more time going into deeper details of their solution and share their journey with Scylla. Okay, without any further delay, I'm glad to hand it over to Kirill. Welcome back, Kirill.
Hi, Serge. Can you hear me?
Yes.
Thanks for doing an intro for me. My name is Kirill Alekseev, and today I will tell how we build a high-load storage of user sections with Scylla and HDDs. So I'm a software engineering team lead in the largest email service provider in Russia. I graduated from Lomonosov Moscow State University with master's degree in computer science last year, 2 years ago actually now. And I do love coding, music, and parties. So I say that we're the largest email service provider, but let's talk numbers. We have 19 million unique real users every day, and we have 47 million unique real users every month. Every minute, we receive 1 million new emails. So let me give a brief overview of what you're going to hear today. Actually, as Serge pointed out, I have already given a part of this talk at Scylla Summit, but I was limited in time there, so I had to skip some technical details. So today's webinar consists partly of what I have already delivered at Scylla Summit, and also I will dive deeper into some technical details. So first I will start with the service overview. I will give you some overview of what we're going to talk about from user side, from business side. Then I will give you the data model we use in Scylla, along with the cluster specifications. Then I will give you the details on application. I will tell how we optimized it to be highly available and how we managed to reduce latencies. Then I will dive deeper into using Scylla with HDD setup. Actually, Scylla is not recommended to be used with HDD, but using SSD would be kind of costly for us, so we decided to give it a try. And we did face some problems, but we managed to solve the crucial one, and I will discuss those problems along with the possible solutions to them. And then I will be happy to answer all your questions. So the first section, brief overview of the service. Let's say that user commits some action in the mailbox, like user reads a new message or probably sends a new message. Every such action we store for possible further use. For example, user may want to check from time to time what happened in the mailbox in time of his or her absence. So we provide our users with such functionality. You can see an example of interface, a screenshot where user can see what happened in the mailbox. So basically, actions history is just a time series of actions stored by email. Every action has its user that committed this action, has time when this action has been committed, IP address from which the action has been committed, project ID, which is kind of ID for a client who wrote this action. For example, it can be IMAP server or probably POP3 server or our storage or something like that. And event ID is an ID for a particular action, like read a new message or send a new message or maybe change signature, etc. So there is an API. This API can handle write and read requests. There is a bunch of clients that use this API. These clients write actions by user and get a list of actions by user. And basically this API goes to some storage. And we used to have a custom storage developed by us. So this service handles 65,000 writes per second at peak load and around 50 reads per second at peak load. So you can see here that writes prevail like 1,000 times. And this is the main point why we managed to use HDDs, because reads are significantly lower. So why at all we decided to change anything? As I have already said, we used to have a custom storage, which we developed ourselves. And first of all, it had poor scalability, which means that we had to add too many nodes to handle the increasing traffic. The next problem that it was kind of difficult to maintain, and by that I mean some administration procedures like adding a new node, like resharding, rebalancing the storage, like doing repairs and so on. And also, since we developed it from the beginning, it did lack some many must-have features like secondary indexes, tunable replication, etc. So what we decided to substitute it with Scylla. And now I will give you details on our data model, on our cluster and hardware specifications. So we currently have Scylla in 2 data centers. We have 4 nodes in the first one, 5 nodes in the second one, and we have replication factor equal to 1 inside each DC. We use consistency level equal to 1 for both writes and reads. This works good for us because usually there are no errors, no timeouts, all writes succeed to both DCs. And even if it does not, it's okay for us to serve inconsistent reads for short period of time. And since we have 2 data centers, we want to be available if one data center goes down. So that's why we use consistency level equal to 1. We run still on bare metal machines, packed with 2 Xeon 6230s, 192 gigabytes of RAM. And we have 2 separate drives, one large RAID 10 array of 10 HDDs of size 16 terabytes for data, and a separate array, RAID 10 array, small SSD array for commit logs. And you can see here that we do kind of replication at drives level. So replication factor equal to 1 inside HDC works okay for us. And all the nodes are connected with 10 gigabit network. So this is how the column family looks like. So as I already said, every action has like its user, time when it was committed, project ID, event ID, so on. Basically, every partition is just a list of actions sorted by time, and every partition is identified by user, year, week, and project. Here's an example of select query. So client must provide user, year, week, and project. Limit is an optional parameter, and with this query, still returns a bunch of actions committed by some user. We use time window compaction strategy. Our data is time series, so time window compaction strategy works good for us, and it gives us the best possible write amplification, the minimal one. We set the time window size to 1 week, and compacting 1 week of data takes about 3 hours, which I think is just great. And we never expire data. We store our data that we have ever written, so we set no TTL. Various other options that I find worth noting. We tried different compression settings. We decided to go with LZ4 compressor with chunk size equal to 64 kilobytes. It works good for us in terms of compression ratio. It compresses data 4 times on production. And also it's good in terms of CPU consumption. We started with the default value for Bloom filter false positive chance equal to 1%, but then we found out that on reads still had to traverse too many SS tables, which would slow down our reads. So we decided to decrease it 10 times, and it works okay for us. So you could see that we store all data by user, but let's say that, for example, our security team wants to check if there have been multiple authorizations to multiple users from the same IP address. And in this case, we would have to provide an ability to read by secondary key. So Scylla has an out-of-the-box feature called secondary indexes. And this did not work for us because it would involve an ambiguous number of network requests, because secondary index is just kind of pointer into primary key. So after reading the secondary key, you have to read all the data by primary key, and those partitions can be stored on different servers. And also that would include incur a lot of random IO, which is bad for HDDs. Another approach could use materialized view, which is kind of similar to secondary indexes, but that would require read before update for every write operation. And with our write rate, it would just kill our HDDs. So we had to go a different way. We decided to create a separate table, substitute a primary key with the secondary key there, and duplicate write that table from our application. So this is how the column family for this separate table looks like, how the scheme looks like. And basically, the user field is just substituted with IP field in the primary key. Of course, this approach requires twice space, but this is okay for us because we use HDDs which are cheap. And also, this approach requires twice write load. And this is also okay because writes and Scylla are mostly sequential, and HDDs work good with sequential access. And since all data is stored kind of continuously on disk, when we want to read a bunch of actions by some IP address, Scylla makes a continuous read from disk. This gives us predictable performance on reads. So here's an example of insert query to this column family. It's basically the same, just the order of parameters is different. And here's an example of select query. Everything almost the same, except that instead of user, you have to provide IP address, and this query returns you a bunch of actions committed from some particular IP address by multiple users. So the given cluster of 9 nodes can handle almost 250,000 writes per second, probably more, we just never tested, with 95th percentile of timing equal to 1.5 milliseconds and 99.9th percentile of timing equal to 22 milliseconds. It handles from 10 to 100 reads per second with the given timings. With this write rate, our cluster grows with 4 terabytes of compressed data every week. So without LZ4, it would take like 16 terabytes every week. Okay, now I will give some details on application. This is the application, the API that goes to Scylla and the clients interact with. I will explain some optimizations that we did to make it more available and to reduce the response time. The first API, write API, this is HTTP. Here's an example of query to this API. So client must provide user, project ID, event ID, IP address, and time. And basically in application, it translates into 2 SQL queries to different tables by action, by user, and by IP address. Nothing special here. So like in every distributed system, our API may experience temporary problems like timeouts or connection resets. So we decided to do transparent retries on every write request. So we do 1 retry per 1 write request. Every retry goes to a different node, different from the first one. And since we have 2 DCs, it actually goes to another DC. And this helps us reduce probability that the retry would fail. And also, in general, you should not retry any write request because you can corrupt your data or create duplicate entries. But we only append new actions. We do not modify the old. And given the Scylla conflict resolution algorithm, last write wins, we're safe from duplicates. So thanks to Scylla. Read API, it is a bit more complicated than the write API. Here's an example of query. The client must provide user, project ID, time range from when to read the actions, and limit. Limit is an optional parameter, how many actions should be returned. So the response is just an array of actions. How does it look in SQL? So user and project ID are provided as is. Then the time range can vary from 1 second to 1 month, and we store all data by weeks. So we kind of have to split this time range to weeks, and then we have to read on application every week. So we deduce the year and week from the given time range. We provide limit as is. And then the next problem is that we use time UID for our time field, and user, the client, provides time range in timestamps. So we have to convert somehow the time range in timestamps to time UIDs. So what we do here is we take timestamp minimum, we step 1 second into the past, and then we take the maximum time UID from this value, which gives us the infimum for the given time range. And then we do pretty much the same to the timestamp maximum. We step 1 second into the future, we take the minimum time UID, and this gives us the supremum for the given time range. This is how it looks like. So I have already stated that time range can vary from 1 second to 1 month. And we have to split this month into weeks. And we can leverage from doing concurrent requests to different weeks. So we can reduce our response time this way. Here is a little problem because you probably can get enough actions from the first partition, from the first week, and you have already made concurrent requests to other weeks, and you will just waste that data. You wasted load on Scylla. So this is kind of trade-off. You possibly create excessive load on Scylla, but you get the faster response time in return. So to optimize the parameter, how many partitions we should read in parallel concurrently, we gathered some data. We saw that on average, to handle one read request, we have to read like 4 to 5 partitions. So we went with 4 concurrent reads, and our timings reduced greatly. Another feature I would like to talk about is the promoted index. Its feature in Scylla still uses promoted index to traverse large partitions faster than in linear time. So if a partition is really quite large, Scylla automatically creates an index for this partition and stores it on disk. So we have quite large partitions, like 500,000 rows in 1 week for one project. This is limited by us. This is the limit we set ourselves. Still, I can probably handle more. So if we read all the partition for every request, not limited the response time anyhow, then the response time of API can be infinite. And this is kind of not convenient for the client because client doesn't know if the API will return some data in like 1 minute or if there is some network problem and it should retry. So to get the predictable response time, we had to put a limit on number of rows that can be returned. And this limit goes straight to SQL query. By this, I mean that we do no limiting on the application. We pass it straight to Scylla, and Scylla returns as many rows as needed, not more. So usually partition has more rows than the limit given. And to signalize the client, we return a special code that is used in HTTP 206 partial response. So the client can make a successive request to start reading where it stopped the previous time. And to make it happen, we return with every response a special value. We call it state. And the client simply passes this state with the successive request. And this is how Scylla understands where to start reading from. So basically, this state is just the time UID of last action, and time is the clustering key for our scheme. So Scylla has the promoted index for large partitions, and we pass this state to Scylla, and Scylla returns us the next portion of data in no time. So this is how it looks like. Client simply provides the state value with the request, and we substitute the upper boundary in the SQL request with this value. So retries and read. Reads are simpler to retry than writes because you cannot corrupt your data with reads. We do one retry per one API request, not more, because we want to limit the response time, and also we don't want to create excessive load on Scylla. Read retry also goes to another node and to another DC. And another optimization that we used, let's say that we had to read like 4 weeks to serve the read request, and we have managed to read the first week. We got some data, but then we failed to read the second week, and we failed to get the limit number of rows that client requested. So in this case, we could return an error and no rows that we have already read, and then the client would only receive error, and probably it would show error for user. User will be disappointed, I mean end user, and I think this is bad. So we decided to return as many rows as we managed to fetch. So the client can show these actions to user and possibly make a background request for another portion of data. So user would be happy and client would be happy. And also another good point here is that if we return no data from the previous request on the error, then user would come again for this data, and we would have read this portion of data twice from Scylla, so we would have created twice load on Scylla. But in case, if we return what we managed to read, then we reduce the possible load on Scylla. So our application is implemented in Golang, and we use GoSQL driver to Cassandra and Scylla. And now I will tell what optimizations we did with GoSQL. So Scylla has kind of streaming feature. It's called paging. How it works: when you read a large partition from Scylla, you don't have to read the whole partition in memory. You can read it by chunks of fixed size. So you read the first page, you process it, possibly you drop it from memory, then you read the second, and so on. But if you want to get the best possible response time, then you should start reading the second page in background when you just started reading the first page, not reading, processing, I mean. So GoSQL has a parameter entitled prefetch. We set it to 99.9%, which means that we make GoSQL start fetching the second page, the next page in background, when we still have 99.9% of the current page to process. So we kind of start fetching the next page in background almost immediately when we receive the first page. And also another thing, we started profiling our application, and we saw that parsing response from Scylla took almost as much time as waiting for response, which is kind of much. And we started profiling memory allocation, started profiling CPU usage, and we saw two things. The first thing was that GoSQL used the Golang reflect package to create maps. The whole problem was around parsing maps from Scylla. So it used the reflect package to create maps, to allocate maps, and this is kind of slow. And the second problem was that all maps were created empty. So when GoSQL started populating it with keys, it had to expand the map, and expanding map also has some overhead. So what we did here, we created a custom unmarshaller for the map, and we created maps with standard tools, not reflect package. It gave us the performance boost, and also we created maps already capable to fit some average number of keys. So we decided that we have like 5 keys on average in every map. So we create maps capable to fit 5 keys. So we are free from overhead that is used when expanding map in runtime. So now I will dive deeper in using Scylla with HDDs. As I have already told, we have a lot of data, and we thought that using SSDs would be just costly. And also we took a look at Scylla at compaction algorithms and decided that it kind of should work with HDDs with sequential access. So we decided to give it a try, although still is not recommended to be used with HDDs. And I think we kind of succeeded, although we face some potential problems, we came with solutions to crucial ones. And now I will discuss both problems and solutions. So the first thing I would like to talk about is the num_IO queues configuration parameter in Scylla. It stands for a number of threads that interact with disks. And in most SSD setups, you most probably would find this set to some large value, like number of Scylla shards. But this would not work with HDDs because HDDs have limited concurrency, and setting this parameter to some high value would just overload the HDDs. So in case of HDDs, you have to find your sweet spot so that throughput is optimal and latencies are still okay. There is a great mathematical result, a little slow. And in this case, it roughly states something like the more concurrency you give, the more time it will take to handle one request. So HDDs can handle one request at a time, most HDDs. And given an array of 10 HDDs, you can have the maximum concurrency of 5 for writes. So you should set num_IO queues to something like 4 or 5. Another problem that we ran into was that node tool repair would take too much time. We started it and it took like a month and it still did not finish. And also, meanwhile, cluster was highly overloaded. So we had to find another way to repair cluster, and we did. So let's say that at some particular moment of time, one node goes down, and you know the exact moment of time when this problem happened. So in case of, in general case, Scylla would have to run a full scan of all data in cluster to find all possible inconsistencies. But this is kind of overkill for time series, because in case of time series, you know the exact moment of time when the problem happened, and these tables are segregated by time. So all the needed data that you need to repair is stored within some narrow set of SS tables. So what you have to do is you just need to go to the node that received all the writes. Then you have to find all the SS tables that contain the needed data. Then you simply transfer all the data to the damaged node, and then you upload all the data to the damaged node by running node tool refresh. So most probably node tool refresh will finish quickly. It will trigger compactions of new data, but this will be the regular compactions and the cluster will not be overloaded. Meanwhile, most probably it will finish in a couple of hours. It mostly depends on how much data you uploaded. But the thing is that you collected some data from other nodes and uploaded to another node, and possibly it contains some data that does not belong to this node. It that does not shard to this node. So to remove this foreign data, you have to run node tool cleanup on the node you uploaded your data to. So another thing I want to talk about is running a full scan. We do run full scans on rare occasions, not on a regular basis. And full scan is considered to be an anti-pattern for SQL, but it just so happens that your database stores the most suitable data to do some analytics or to make some decisions. So it is good if database can handle full scans, at least on rare occasions. Some possible use cases. So let's say that we have an action for authentication, like a user authenticated into authorized authenticated into account. So we want to see how many active users we had last month. So we had to find all authentication actions and then count all unique users in these actions. Or another possible use, let's say that we launch some new feature last quarter, and we have an event for enabling this feature for user, and we want to see how many users activated a particular feature. And I think there can be many use cases for full scan. So the main point here is that we have a lot of data, but we want to do a full scan within some narrow time range, like 1 month, which is many times less than the actual size of data. So we tried a naive SQL approach. By this, I mean just launching a query, like select everything from the table. We tried a smarter approach when we took the whole token range and we split it to smaller sub-ranges, and we tried selecting by these ranges. As I understand, it should have given Scylla a kind of hint how to read data sequentially, but unfortunately it did not work for us as well. So we decided to go our way. We took as a stable metadata, it's an utility that comes with Scylla, and we used it to narrow the original set of these tables to the smaller one, which contains only data for this 1 month. Then we took all these tables collected on the previous tab and we ran as a stable dump on every such table. And the good point here is that you can run multiple stable dumps in parallel. So you kind of have a knob, then you can turn to get the optimal performance. The output of a stable dump is just a JSON. So what you need to do is you have to parse JSON in streaming fashion and collect all the data that you need. But the problem here is that output of a stable dump is a single large JSON. So if we have some huge stable, like tens of gigabytes, it would be encoded as a single JSON dictionary. So to parse this dictionary in general, you have to fit it in memory. You can have a machine with hundreds of gigabytes of RAM to parse these huge JSONs, but this is just inefficient, especially if you have still running on the same node. So let's consider an example of some person who really likes the heavy metal music, and he or she has a really great library of many songs, many albums. And this library can be represented as a single huge JSON object with size of tens of gigabytes. Another point here is that any field can be arbitrarily long. For example, some artists may have like millions of albums. And by this, I mean that not only the whole JSON would not fit in memory, but also any subfield would not fit in memory. But the key point here is that you only need a small subset of fields and you are sure that this field would fit in memory. And let's say, for example, that you want to count number of artists that come from England. So the solution here is just to implement a custom parser for the subset of JSON language. You don't need to parse the JSON in general. You just need to parse some regular subset of JSON grammar. So here's an example how it would look in Go. So we need some lexer that could tokenize the input. Token is an atomic literal in JSON language, like brace or string or comma or something like that. And then you read this in infinite loop. And you know that when you see a token that equals to string origin, it means that the next value is going to be the value you're looking for. So then you check the next value. If it is England, then you increment the counter for English artists. That's how it works. So to implement this, you need a streaming JSON tokenizer that would not fit the whole input in memory. And it turned out that the standard encoding JSON would provide a streaming JSON tokenizer, but the problem was that it consumed a lot of CPU, and CPU became the bottleneck for us. So I decided to implement my own library, go.jsonlex, which parses the JSON in a streaming fashion. It is a drop-in replacement for standard encoding JSON. It has the same interface, but the main point here is that it's 2 or 3 times faster than encoding JSON, and it requires the same memory footprint. So this library let us get the analytics we needed 2 or 3 times faster. So this approach leverages from sequential access to disks. It is the most effective use of HDDs. It finishes in reasonable time. By this, I mean that to gather 3 months of analytics, we had to wait for like weekend, and it works okay for us. And also it excludes network requests, so it is fast and reliable. The obvious disadvantage is that you have to do some coding, but I think that you have to do it once and then you just launch it as many times as you need. And also you have to run it on each node, at least in one data center, on the contrary with using SQL, where you would just execute one query and SQL as such would do all the magic for you. So these were the crucial problems. I think we managed to solve it, and it works okay in production. There are still some lower priority problems that are yet to be solved, like latencies grow during compactions, cleanup, and bootstrap. And latencies also grow when a node is down, but the growth is within a reasonable limit, so it's okay. Also, node is it is slow to bootstrap a new node, but still it works and it finishes in some reasonable time. So you can see that using Scylla with HDD is kind of challenge, but it works if you do some work. And the main point here is that you can save some money, of course. You can save at least $150,000 of capital expenses per 1 petabyte when compared to SSD setup. So we have achieved the following results. We have built a high load horizontally scalable service for storing users' actions with Scylla and HDDs. The given service is able to handle almost 250,000 writes per second with 95th percentile of timing equal to just 1.5 milliseconds with a small cluster of Scylla nodes. We have implemented an approach to serve reads by secondary key with predictable performance. And we have implemented an approach to do full scans in reasonable time on rare occasions. This year, we are going to add third DC to this cluster. We are going to optimize Scylla and clients to get even better latencies. And we are going to integrate Scylla into even more projects. I would like to give my special thanks to Dima and Pasha for helping me build and deploy this service, to Igor for approving the research and development process, to Vlad, Avi, and Rafael for helping me with issues we had in GitHub, in Slack, and everywhere possible, and to the whole ScyllaDB for an awesome product we're happy to use. Thanks for your attention. I'm happy to answer any questions now.
Thank you, Kirill. Excellent presentation. Love it. At this time, we have time for some questions. Feel free to enter those questions in the Q&A window, and we will answer them. Kirill will answer them for you. There's our first question. Kirill, given the high write rates at 240,000 RPS and slow hard drives, does Scylla manage to compact all data that's been written? And how long does it take?
Yeah, that's a nice question, because Scylla is not bottlenecked when serving actual writes. The bottleneck may come when it's starting to compact. And I can say that compacting the whole week of data takes just 3 hours on average, and it happens usually at night, so it does not affect reads or writes. And kind of regular compactions that happen all the time, it does not overload system as well. So compactions are okay with this write rate.
Excellent. The next question, what type of authentications are you using to access ScyllaDB? Is it possible to use Kerberos?
I'm not sure that I understand question. We do not use any authentication from our application to Scylla right now. I guess you can use like simple plain text login password. It is more about Scylla feature, I guess.
Absolutely, yes. The next question, did you try to use consistency level local 1 instead of just 1?
Yeah, I think we tried using that in the beginning, but that turned out to be working bad, I guess, because if one node goes down, we don't have enough replicas in the data center to serve this right in the local data center. So Scylla fails to proxy request to another data center, and the whole write fails. And this is bad for us because system becomes unavailable.
Okay, excellent. Another question. How many spin drives in your cluster and how big this cluster is?
Let me go back to the slide so that the written answer can be understood better. I had a slide on that. This is our cluster. We have 2 data centers, 4 nodes in the first one, 5 nodes in the second one. And every node has 2 separate RAID arrays. One is for commit logs. It's a small SATA SSD array, and it handles that write traffic. And another separate RAID 10 array of large HDDs, 10 HDDs of size 16 terabytes for data. So this way, we do not throttle our HDDs with write, and still it is cheap because the ratio of HDDs to SSDs on one node is like 80:1.
Excellent. Another questions. Why do you mirroring your HDDs if you have data replicated at the cluster level?
So I consider replication on cluster level not only as the safe mechanism to restore data from, but also as more like, I would say even more like a mechanism to scale your reads. So we have a couple of data centers to scale reads and also to be available if one data center goes down. And we use replication on hard drive level because still bootstrapping a new node from an empty node, it's kind of slow because we use HDDs. So we want to reduce occasions of bootstrapping a new node from the empty node to the minimum possible. So if one hard drive goes down, we can substitute it without bootstrapping a new node because it would be restored from RAID array. So that's why we use arrays.
Excellent. And another question, do you have to run your manual repairs every time when you restart Scylla, or some temporary network problems, for example, occurs?
No, we don't have to run those because we use the how it's called, hinted handoff feature. It's really handy. It's kind of engineering solution, but it helps you like in 99% of times. Hinted handoff is a kind of local queue on every node. If one node cannot replicate to another node, then it saves a write request locally on its disk, and then when that node goes up, it simply retransmit the failed request.
Excellent. Let's wait for more questions. Excellent. It just came up. What hardware resources is the current main bottleneck for your database?
I think it's hard drives. It's still hard drives. We are kind of happy with the throughput we get, but if we wanted to push more, then we would have hard drives as bottleneck.
Another question, what is your current data footprint looks like?
Sorry, what does it mean, data footprint? How many data we collect?
I think so, yes. Currently storing on hard drives.
So we save 4 terabytes every week of compressed data. It is compressed by LZ4. So we grow our cluster with 4 terabytes every week. And we set no details. So the cluster is constantly growing in space. And currently, let me count. I guess we have like 200 or 300 of terabytes of data.
Hundreds of terabytes of data. Excellent. Another question, why did you use time UUID for a time range?
So the alternative was to use simple time field. But let's say that there is an action. Let me show the scheme. Maybe this way it will be more easier to understand. We have some action that we have two actually separate actions that have all the parameters same, but those are actually two different actions. Like user managed to read two different messages in the same second. So all the fields will be equal, but still those should be different actions. If we use simple plain time, then Scylla would leave only the last one because all the fields would be equal and still use last write wins. So last write would stay. But time UID consists of two parts. The first part is the time when is the actual time, and the second part is the UID, which gives some kind of random. So the actions that are the same and happened at the same time, it would be different. It would have different time UIDs, and it would stay both.
Excellent. Yes, there's another question, and I think you already answered that one. The question was, did you try to use consistency level local quorum instead of one?
Well, I cannot use quorum because we have only 2 data centers and we have replication factor equal to 1 inside each DC. So that's not the case now. We will add a third DC and we will certainly use quorum. And also, I think I missed one question. Somebody asked about running manual repairs. Yeah, I answered that one. Okay.
Yeah, you answered that one. Yes, and basically another question for the replication factor 1. Why are you storing data in the replication factor 1 instead of using like a more kind of adapted for replication factor 3?
So we store replication factor of 1, but we have 2 data centers. So we kind of have 2 copies of the same data. And I refer to replication factor as a mechanism to scale reads, not like some safe mechanism in most cases. To be available if one node goes down, it is okay for us to have just 2 data centers right now. And we do not have to have more reads. We don't have to handle more reads. So we do not have to increase the replication factor. So that's why we use replication factor equal to 1.
Excellent. And one more question. What compression settings do you use for your SS tables?
I can show that. We tried different settings. We tried snappy, deflate, everything that was there. I did benchmarks. I kind of scripted altering the scheme, running memtable flash and compact, and then I measured the time it took to recompact, which means recompress all the data, and LZ4 with 64 kilobytes won because it was fast. It had lower CPU consumption, which is good for us because we will not have bottleneck in CPU because our bottleneck is HDD. We have nodes with great CPUs, and we don't have CPUs bottleneck, we have HDDs bottleneck. Also, this gives us the appropriate compression ratio. That is compressed like 4 times in production. So this is just work good for us.
And one more question I see that only one table is action. Does database contains other tables? Is Scylla depraved for this task alone?
We have actually 2 tables. Scylla is used alone for this service. I mean that it only stores actions and it doesn't store any data for other teams or other services. It only stores actions, but it actually has 2 tables by different primary keys. This way, we managed to implement reads by secondary key with predictable performance.
Excellent. Excellent. Thank you, Kirill. I have no more questions. So once again, thank you, Kirill, and thank you everyone for attending our webinar. Just a reminder that we're going to share the recording of this webinar, and we will email you the link and to the recording and link to the slides. Once again, Kirill, thanks again for participating, for showing this great solution that you have. And yes, and thank you participants for attending. Hopefully you learned a lot of valuable information during this webinar. Thanks again.